Hi, this is lecture 27. This is part 3 of theory of integrations. So, we have seen what is the notion of Darboux integrable function, Riemann integrable function. Then we have said that these two are same. Then we did some examples and some properties. Now we will do one more example of a function that is not Riemann integrable. Let us see. So consider the function a comma b some interval, closed interval, and we are defining for x in a b, we are defining it to be 1 if x is rational, and we declare it to be 0 if x is irrational. Now let us check if this is a integrable function or not. I already said it is not integrable, but we will see what is the reason why this is not integrable. So before proceeding to anything else, let us take some partition and then check what is the UPF and LPF. This is EF. Let us take a simple partition, the basic one, just two elements, P is equal to AB. A partition should contain the endpoints of interval, so I have to include those, and I am not taking any other element, just these two. Let us compute UPF and LPF for that. So what is UPF? That is equal to, I have to restrict F to this interval containing A and B, take supremum of F restricted to A comma B times length of this interval. So this is B minus A. See, observe that F takes only two values, either it takes 1 or it takes 0. In this interval there will be rational number. So F takes 1 in this interval, supremum, see this image of this is just of two elements 0 and 1. 1 belongs to the image because this contains a rational number, 0 belongs to this image because this interval contains a rational number. So this thing, the image of F restricted to AB is just two elements at 0 comma 1. So supremum is 1 for that, and we have 1 times B minus A is B minus A. Let us compute LPF. What is this? Infimum of F restricted to A comma B times B minus A. As I have said that image of this F restricted to this interval is just two elements at 0 comma 1. So the infimum is just 0. 0 times B minus A is 0, so I am just writing it to be 0. Now here these two are very much different. So what is the notion for integrable function? A function f is to be integrable if there is a partition such that UPF minus LPF is less than epsilon. Here it is B minus A minus 0, which is simply B minus A, that is I mean, if this has to be, if this should be the appropriate partition for the integrability, then this should be less than epsilon. But if I take A comma B to be a very big interval, then this is not less than epsilon. Anyways, we are not trying to prove that it is true. We are just checking that whether this will immediately say that it is integrable or not. This does not say it is integrable, because for this partition we have B minus A minus 0 as B minus A, that is if I take A comma B to be 0 comma 1 and epsilon to be half, then B minus A is just 1 and 1 is less than half, is it does not look like it is the case. So this thing is not useful to conclude it is Riemann integrable or not. Now let us take one more partition. Let us take a partition with 3 elements. It should contain A and B, of course. Let us take some random elements C, A, C and B. Now what is it? we are supposed to do the same thing. Again UPF and LPF, let us check that. What is UPF? F restricted to this interval, take supremum of that and take the length of this interval. So, supremum of F restricted to A comma C times C minus A plus again supremum F restricted to C comma B times B minus C. Again this interval contains both rational and irrational numbers. So, F restricted to this interval, the image of that will contain 0 and 1 and just contain only those two elements 0 and 1 only, because if you look at F, the image should contain only 1 and 0, only two elements are in the image of F. So, here also it is only two elements, supremum is 1 times C minus A, let us write that down, there is a plus. This also contains both rational and irrational number. So, this image will contain only two elements, supremum is 1 times B minus C, let us write that down. This C and this C gets cancelled, so this is B minus C. Now, what is LPF? I am not writing again the same formula, but the idea is following. I have to replace this by infimum. This will contain only two elements 0 and 1, infimum is 0 times C minus A is 0, so 0 plus again the same thing, but this is replaced by infimum. This contains only two elements, the image contains only two elements. So, infimum is the least element, that is 0 times B minus C is 0, so this is equal to 0. If you observe, for partition with two elements we got UPF to be B minus A, LPF to be 0. For partition with three elements we got the same thing, UPF is equal to B minus A and LPF is equal to 0. Is it the same case with any partition? Let us check that. Let us take a partition B is equal to A, this x0, x1, so on, xn is equal to xn minus 1 and xn is equal to B, comma xn is equal to B. There are n elements in the not n plus 1 elements in this partition. Now, let us compute UPF. What is UPF? The same thing, take F, restrict to this interval x0 and x1, take supremum, take length of this interval. Again this interval x0 comma x1, they are not same, that is what partition is. So, x0 x1 is a closed interval, it contains both rational and irrational number. So, when I restrict F to this interval, the image contains two elements again 0 and 1. So, supremum is 1 times length of this is x1 minus x0 plus I have to repeat the same thing. So, then the next thing is I should take x2 minus x1, next thing x3 minus x1, x3 minus x2, so on, plus xn minus 1. Observe, in the first step x1 is appearing 2 times with a minus sign, so that gets cancelled out. I think you can guess what is happening here. So, in the next thing there will be minus x2, this will get cancelled out. So, what is remaining is xn minus x0, not x1, xn minus x0, xn is B, x0 is A, so that is B minus A. Let us look at LPF. What is it? Again the same thing, we have to restrict F to this interval, again this contains two elements 0 and 1, infimum is 0, 0 times this is 0, 0 times this is 0, 0 times this is 0, it is just 0. So, what did you observe here? For the function f that I have mentioned just now, where is it? Here. For this function, whatever partition you take, UPF is equal to B minus A, LPF is equal to 0. And what is UF? UF is supremum or infimum. You do not remember the formula again. At least see now there is it is not a good idea to remember the formula. You again you take two partitions P and Q, assume Q is a refinement of P and then check yourself whether UPF is greater than or equal to LPF or UPF is greater than or equal to UQF or the other way. then compute this, verify which of this is that is true, then you will be able to guess, you will be able to know what is the formula for this. Do this for a couple of times, maybe 20-30 times, then you will remember the formula. So whatever it is, UF is the supreme or infimum of UPF, where P is any partition, but that set contains single element. So supreme or infimum is just the same elements. This is B minus A. Similarly, LDF is just 0, and B minus A is not equal to 0. So this says F is not a Riemann, not integrable. So this is an example of a function that is not a integrable function. Okay. Now let us check the properties that we have proved or assumed for the previous ideas. Look at continuity. If I take any function f from u subset of R to R, if I restrict f to some subinterval, appropriate subinterval, then I know continuity of this implies continuity of any restriction. Maybe much before that, you can take any sequence, say n to R, say A, and if you take a subsequence, what is subsequence? Just some map from n, we are just taking the composition A F. If you compose if you take A compose F, then this is a subsequence. F has to be nice, of course. Then if I know A is convergent, then this is convergent. So subsequence is behaving nicely, preserves convergence, and what else? We know about differentiability. Suppose I take a function f R to R, and f it is differentiable, and if I take a open subset of U, and if I restrict f to that, then the restriction is differentiable. So let us check if it is the same case with the integral function. Suppose I take a function f a comma b to R. If I know it is integrable, if I take a subset of this of the form c comma d, say f restricted to c comma d, is a map from c comma d to R. If I know it is integrable, does it imply this is integrable? See, some of you might be thinking, see, what is the problem? It is true for this and this and this. Why do you have to check this? The problem is the following, that see, this kind of thing, the appropriate counterpart for series is not correct in the following sense. Suppose you take a series summation a n is equal to 1 to infinity. Suppose I take a series and I know it is convergent. Now what I do is the following, I will take a subsequence of this, which means I am just composing with a map, some nice map. I will take a subsequence of this and look at the corresponding series. Even though this is convergent, this need not be convergent. We have the same previous example that we used many times. What is it? Minus 1 power n by n is equal to 1 to infinity. This series, we know it is convergent, but if you take the corresponding subsequence, you take the map n goes to 2n, then the corresponding series for this is the following. Let me write down this 2 correctly. This is 2. So the corresponding series is summation minus 1 power 2n, which means I don't have to write anything, it is simply 1 by 2n, n is equal to 1 to infinity. If this is convergent, then if I remove 2, that also should be convergent, and I already know this is not a convergent series. So subsequence preserving convergence of series is not true. So now we are slightly afraid whether this is true or not, because integration we are trying to relate with the series. So for series it is not true, for this is it true? So that is the problem. So we cannot take it very easily, we have to check. Let us check that now. So now what the setup is the following. I have a function a comma b to r, and I know it is integrable. I am trying to check if the restriction f restricted to c comma d, is it integrable? That is what we are trying to check. Now see, I am not asking to compute the integral. So if I do not have to compute the integral, I can simply use the Riemann condition. What is it? So to prove that it is integrable, all I need to do is the following. I need to look for a given a epsilon positive, I need to look for a partition p epsilon such that u p epsilon, let me write down this as g just for convenience, g minus L p epsilon g is less than epsilon. This is what I am supposed to prove. Now I need to get a partition with some property. We know f is integrable. So given epsilon positive, the one which we fixed here, given this epsilon positive, there is a partition for this AB with some property. What is it? So let me call this as here we are looking for a g, just to differentiate. This is what we want, but integrability of f is a partition PE, or maybe I will write down that as f also. This is a partition of AB such that u p epsilon f minus L p epsilon f is less than epsilon. This is what it is. So how does a partition of AB look like? It starts with A, writing as x0, x1 dot xn minus 1 is equal to xn, sorry b is equal to xn. Now suppose we are looking for a partition of CD, which means we are looking for some elements and hoping that for those elements of C comma D, this turns out to be true. That is what we are trying to see. Now this is the partition, and C comma D subset of this. So there may be elements here which are elements of this interval. In the sense there may be some I belongs to 0 dot n such that xi belongs to C comma D. Right, this possibility is there, or it may not be there. There are two cases, either all elements of this are elements outside C comma D, or there may be some elements that are inside C comma D. Let us do both cases one by one. Suppose that this does not contain any element of this interval. So then what we will do is we will just add those two elements. So now p epsilon f is x0 x1 dot xn minus 1 is equal to x comma xn, b is equal to xn, this is equal to a. Now we will add C comma D, C and D both to this to get a refinement of that. So that I am calling as q epsilon. So now the question is, where should I add? I should look for I 0 less than or equal to n minus 1 such that xi, see we have said that none of the elements are elements of C comma D. So we are looking for some I such that xi is less than C, of course less than D, less than xi plus 1. This is what we are looking for, the appropriate I. Then we will add C comma D in between this. So let me do that, x0 x1 dot dot dot. After xi, I will add c comma d. See why I am trying to focus so much on this. By definition, a partition is a finite set of finite subset of the interval, such that these elements are in increasing order. So I cannot add c and d here. So this is obvious thing to do, but still. So I need to look for some I for which xi is less than c and that is less than xi plus 1. In between those I will add c and d. So xi c comma d xi plus 1 dot 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 xn. Now the question is, do I have similar thing for this? You already know that. Okay, suppose I take a refinement of a partition, then u q epsilon f is less than u p epsilon f or equal to, that is allowed. And what about L q epsilon f greater than or equal to L p epsilon f. Again, this we have done multiple times already, in 2 lectures only I have done 3-4 times. So now what we have this property. So let me combine these two. Before combining, let me change the sign. This is minus, then I have to change this into less than or equal to. So what do we have? This plus this is less than or equal to this plus this. We know UPF, we know u of this minus L of this is less than epsilon. So that implies u q epsilon f minus L q epsilon f is less than epsilon. So either one can use this partition, or you can take a refinement by adding c and d and take this partition. For any of those two, we have the same property. U minus L is less than epsilon for this partition QE and also for PEF. Now suppose there is some element, coming from CD in this partition. Then what do? Again you need to check for some I. Let me write down that. So suppose P epsilon F is equal to x0, that is equal to a x1 dot dot dot. See here C and D are not elements of this, so there is some I for which xi is less than c, less than xi plus 1. Now we are assuming that there are some elements from the interval CD. So let me draw this. So this is AB, this is C, this is D. So suppose x0, x1 and so on. I need to look for some I for which xi is less than c, less than xi plus 1. Then at that point I will add the corresponding c. If c is not there, I will simply add that. Then I am looking for some j such that xj is less than d, less than xj plus 1. See, this is nothing special about this, we are only making sure, or one can of course just simply add c and d for this PEF. Let me finish this. xn is equal to b for this PEF, and then write down that in the increasing order. So this is maybe more time consuming than that, but still I am saying this only to give you some more clear idea of what actually a partition is. It is an increasing order of elements from the given domain. So yeah, we will look for some I and j with this property. This is j, not I, this property, and then we will simply add c and d. So in any case, and that will also be refinement of this P epsilon f. So in both cases we get some partition, that all I am calling as QE, Q epsilon, some partition x0 is equal to a x1 dot 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 x I c. Let me write down the partition. Let me write down the elements coming from the partition from the subset of c comma d in as y1 dot 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 y say m ym is equal to d, and then I will write down the remaining part elements. Then what is remaining? With the index is not very correct here. So there is m plus 1, there will be something else. So we will write down the remaining element. Let me write down, start with L xl dot xn is equal to b. This index you need to fix the index correctly. In any case, we have a partition q epsilon of a comma b such that u p epsilon, not p epsilon, q epsilon f minus L q epsilon f is less than epsilon. Now some of you might be already guessing what I am going to do. See, this gives a partition, this is a finite set in increasing order, gives a partition of c comma d. Let me call this just this as what should I call it as R. So now we have partition R of c comma d. Let us check what happens to R, the restriction I was calling as G, Rg minus L of Rg. Let us see if this has any relation with epsilon. Do you have any relation between these two? Observe, how do you write down this UQEF minus LQEF? F restricted to this interval, take supremum and then take the length of this interval. So that is let me write down first few elements, supremum of F restricted to some interval times the length of that interval, plus again supremum so on. Then observe that R is a part of this partition. So from here in this portion I do not have to write down supremum again, I will simply write down as URG plus so on plus URG, then I will write down the remaining thing, so on plus supremum times length of this interval. That is what U q epsilon f is just this, minus what is L q epsilon f, same thing, this same thing replaces that by infimum. So infimum f restricted to some interval, length of that interval, not plus, minus dot minus L R G plus not plus again, minus, this is minus minus infimum of f restricted to some interval times length of the interval. What we know is, we know this minus this is less than epsilon. Observe, consider this part, supremum minus infimum of same function, supremum of f restricted to a x1 minus infimum of f restricted to a x1 times x1 minus a. I am only writing the first part, but the same thing is true for any other element. See, observe that even though if is positive or negative, it does not really matter, supremum is always greater than or equal to infimum. So this difference is always positive, and this is increasing in increasing order, the partition is in increasing order. So this is positive, so this whole thing is positive. So this part is positive, the next part is positive, everything is positive. So what I have is this I am leaving as it is, I am not changing it. So U R G minus L R G plus some positive number is less than epsilon. What does it conclude? This imply U R G minus L R G is less than epsilon, right? A plus b is less than epsilon and b is positive, this plus a is less than epsilon. What does this say? This says G is integrable on CD. So let me write down that G is integrable function. G is a map from C comma D to R. This is simply the restriction of f to this subset C comma D, subset of A comma B. Okay. So now what we have seen is the following. Whatever we were thinking, whatever we were afraid about the integrable of restriction map. See, where did I mention that? Here. For series, if I take subsequence, if I start with the convergence series, if I take a corresponding subsequence and then take the corresponding series, this may not converge. So that gave us some feeling that this may be true for the integrable function also, but it turns out that that's not true. If I take any function f that is integrable, if I take a subset of, if I take a restriction of f to some subset of a comma b, that is still integrable. See, these two are not actually really same. I mean, subsequence, taking the subsequence and then taking the series is not really same thing as taking a restriction, but we were slightly afraid, which was not necessary, but it's a good to know proof of that restriction is integrable. Now what? Suppose we take a function f and I know it is integrable, then I know for any subset of the domain the restriction is still integrable. F is a comma b to R is integrable. This implies for any c comma d subset of that a comma b, the result is the restriction is still integrable function. A special case will be the following. So f restricted to a comma c, c is some fixed element of a comma b. So I am just restricting f to this interval, so that is integrable. This is c, integrable. Then f restricted to c comma b is integrable. So now the question is the following. Suppose, see, we are starting with the case that f is integrable, so that implies these two are integrable. A comma b is a union of this and this. It is not disjoint union. There is a single element that is common for both. So a comma, the domain of this function is a union of these two subsets. The question is, do I know how to compute f? If I know something about integrability of this, integral of this and integral of this. So the question is the following: is there any relation between integral a comma b f or fx dx, integral a comma c fx dx, integral c comma b fx dx? This whole thing, a to b the corresponding interval, is a union of this and this. All we are asking is, does it help us to compute this once we know this and this? That is the question we are trying to we'll try to answer. Okay. So now using this, we will try to say something about this. It's not really clear where to start. We'll start somewhere. So f restricted to a comma c, I am writing that as g just for convenience. G is equal to f restricted to a comma c, and I am writing as h the function f restricted to c comma b. See, g is integrable. So what do we have? Given epsilon positive, there exists a partition p epsilon g of a comma c such that u p epsilon g minus L, this is g, L p epsilon g is less than epsilon. Same thing for the same epsilon, there exists a partition for cb that I am writing as p epsilon h such that u p epsilon h minus L p epsilon h is less than epsilon. Now what? These two partitions gives a partition of a comma b, because what are these? These are elements of AC and these are elements of C B, and both of them will have a one point as common C. So these two subsets we are taking the union and removing one C. That's how you take union, right? So there is some common point, you will not take it, you will take only one, only once. So P epsilon is simply union of P epsilon G union P epsilon of H. Then let us compute U P epsilon F minus L P epsilon F. See, what you know is the following: given epsilon positive, there exists some partition, not necessarily this of this, such that U minus L is less than epsilon. That much we know, but it is not necessarily true that it is that this is true for the partition P epsilon that we are constructing from these two partitions. So I don't know whether this is true or not. All I know is there is some partition. If I replace that by Q and Q, I know this is true. U Q F minus L Q F is less than epsilon, but I don't know whether this is true or not. So let us check that first. Whether it is useful or not, that is secondary. Well, let us just check. What is this? This is again supremum of F restricted to the first interval of this, then the length of the interval, and we will repeat again and again. Similarly, this, see, P epsilon is union of P epsilon G and P epsilon H. So this thing is just U P epsilon G plus U P epsilon H. It is just sum of these two elements, that is all. Similarly, this is the sum of not U but L. So L P epsilon H plus L P epsilon H. Oh, this is G. This is G. There is a minus here, so we will put minus here. There is a minus, and this is a minus. So this thing is actually this thing. What we know is the following: UPG minus LPG is less than epsilon. So this is less than epsilon. There is one more extra thing: UPH minus LPH, that's less than epsilon. There is one more epsilon, that's equal to 2 epsilon. And we know 2 epsilon is as good as epsilon. So given epsilon positive, we got this inequality. So observe the following: we assumed that f is integrable, then we concluded that f restricted to the intervals AC and CB are integrable. But let us not assume that f is integrable. Let us assume that f restricted to this is integrable, f restricted to this is integrable. Here we are calling that as G and H. Let us assume G and H are integrable. Then this observation says that f is Riemann integrable. Why? Given epsilon positive, there is a partition such that this minus that is less than epsilon. What does it say? It says f is integrable. So yeah, this result I will mention the notes. If I know, if I take any function, of course bounded, such that f restricted to, suppose that AB we are writing as union of two subintervals, and the restriction is integrable in both cases, then the function is integrable. Yeah, let us now come back to this. It was a diversion. Now what we are trying to see, is there any relation between let me call this as for G, this is integrable. So for that UG is equal to LG, UG is equal to LG, H is also integrable. So UH is equal to LH. We are trying to see whether UF, F is also already integrable, is equal to LF. We are trying to see if there is any relation between this and this. Let me finish this LF. Now observe the following: now you need to remember the formula for UF and LF also. UF is infimum of UPF where P is any partition. So, in particular for this PE that we have considered here, where is it? This one. What we have is the following, that U F is less than or equal to U P epsilon F. Similarly, LF is supremum. So, what we have is L P epsilon F less than or equal to LF. Okay. Now, what we have is the following, we have L P epsilon F less than or equal to LF is equal to UF less than or equal to U P epsilon F. What we know is this minus this is less than epsilon. Let us keep it aside for some time. Observe that where did I mention about LP epsilon F? I have mentioned that LP epsilon F is just the sum of this and this. Let us write that down. L P epsilon F is equal to L P epsilon G plus L P epsilon H. Again, this is less than or equal to this I am writing as, of course, this is less than or equal to L, the integral of G. So, integral G, this is less than or equal to integral H, this is less than or equal to U P epsilon G plus this thing is L P epsilon H. Again this thing, oh sorry, this is again U, this sum is just U P epsilon F. Observe that let me write down that completely. So, L P epsilon F less than or equal to something less than or equal to U P epsilon F. So, now what we have is the following, we have two elements say A comma B such that the length of this is B minus A is less than epsilon. Now, we have other two elements say C and D, both of them of this property. Then this condition B minus A being less than epsilon imply C minus D is also less than epsilon. See, all I am doing is saying is the following, you take some interval A comma B, suppose I know that distance between them is less than 1, suppose I take any two elements not necessarily in this order, it's in the reverse order, any order, distance does not really matter about the does not really care about the order. So, B minus A less than 1 implies this difference is less than 1 or less than 1, yeah, that is all. So, we use the same trick here. So, what we have is UPF minus LPF is less than epsilon, and there are two elements. See, this is what is this is integral F is integrable, so this is same thing as this. So, there are two elements integral F and this, both of them lie in this interval LP epsilon F, UP epsilon F. So, their difference should be less than epsilon. Why we have already mentioned that we have this property. So, both integral F and integral G plus integral H lies between this interval coming from these two. So, the difference integral F minus integral G plus integral H is less than epsilon or the corresponding modulus. Observe that this portion does not have anything to do with epsilon. Whatever the epsilon is given, this thing is always less than epsilon. So, because epsilon is arbitrary, this implies that integral F is equal to integral G plus integral H. So, what does it say? If I take a integrable function F restricted to two subintervals whose union is the domain of the interval, then integral of F on AB is equal to integral of the restriction AC and CB. So, this is a property of integrable functions. this can be used to conclude to compute some integrals. Now I'll add one more result, the fundamental theorem of calculus. I'll add in the lecture notes. Due to some time constraint, we are not covering it in the video, and I'll add one or two more extra results about integrable functions, and that's all for theory of integrable functions. In the next session, we'll talk about metric spaces. That's all.